Alright, so in this video today I'm going to be showing you how to use an in-cylinder pressure transducer to diagnose engine performance issues. And so first of all I'm going to show you the setup that we have here. So on this vehicle, this is a 2013 Ford Fiesta. And so what we've done is we've removed the spark plug out of cylinder number 1 here, and in the pressure transducer we're using is the Picoscope WPS 500X. And so in the kit it has this hose, and you make sure you put the right adapter that fits the spark plug that you pulled out. So we got that threaded in there like that. And then you can see we have the pressure transducer plugged in and turned on to range 1. And then if it's having trouble holding power, I usually leave this USB cord plugged into the laptop like that. And then obviously we have our BNC lead going up to the Picoscope on channel A. Now, to protect your coils and stuff like that, I really enjoy this tool right here, which allows me to keep the spark plug plugged into the spark plug wire or the coil, whichever one you have, and it just threads into this, and this is grounded, and I have it over to battery negative. You could also just run it to chassis ground. Okay, and then on channel B, I have this secondary ignition probe over that wire so that we can get a sync signal, and that is just grounded right there. All right, so on the Picoscope itself, as far as setup goes for channel A, you got to make sure you choose that probe. So it is right down here, WPS 500X, range 1. And then for channel B, same thing, go to the probes menu, and we're using that secondary ignition. And for this test, it doesn't really matter which one of these you pick because we're just using it as a sync. So we'll just leave it like that. And then as far as our ranges go, we'll leave those as the default. And then as far as time, I usually like to capture quite a bit on this. So I'm going to turn this up to like 5 or 10 seconds per division so that we can capture a bunch of data. That way you can check the engine at different RPMs, maybe even do a cranking on this if you want to. So let me go ahead and start it, and then we will analyze the capture. Okay, so we've started the engine, and you can see we're starting to get that waveform. I would like to get more detail, so we are going to drop this range down on channel A down to, that's probably good. Now just keep in mind that when you rev it, it's probably going to go above that. So this is a good range for just idle, but when you rev it, you're probably going to need to go up to this range because your compression will triple under wide open throttle conditions. Okay, so maybe we'll leave it right there, and then I'll do a couple snap throttles, and yeah, then we'll come back and look at it. Okay, so we have finished capturing our data, and we are now going to analyze what we have. So before we zoom in on anything, I just want you to see what we did out in the shop. So right here, we were just idling the engine. And then here, I revved up the engine to about 2,500 RPM, and I held it. Right here, I let off, go back to idle. And then I did a snap throttle, back to idle, snap throttle, back to idle, and then I shut it off. So we have everything we would need to really analyze this compression waveform, except for maybe the cranking. We didn't do cranking, but I'll talk about what differences you might see in that. Okay, so let's zoom in. I'm going to zoom in on the idle first, and the first thing we want to do is just kind of understand what we've captured here. So I'm going to pick a couple events here. Notice on channel B in the red, we are picking up the spark for cylinder number 1. It's a waste spark system, so that's why we're getting spark happening here as well. But this is cylinder 1 spark, this is cylinder 1 spark, and so it lines up with our, close to our compression peaks. Okay, so when you're looking at pressure in this cylinder, you got to keep in mind that we're not running in this cylinder, right? We've taken away spark, and so we're not getting an actual power stroke. All we're watching is pressure or volume changes inside the cylinder. So right here, right, we pulled in a bunch of air, and now the piston is traveling up, and we are compressing that air up to this point. So this is when the piston reaches top dead center, and then it turns around, and all that pressure that we created starts to decompress. At this point right here, you can see the 0 mark. And at that point, we now are going into a vacuum. And then right here, the exhaust valve opens and back pressure from the exhaust system starts to enter the cylinder. And then right here, back pressure in the cylinder is equal to the exhaust. So this whole part is exhaust, and then right about here, and I'll get more specific on the numbers in a minute, right about here is when your intake valve will open, and then here your exhaust valve opens. Now we go back into that vacuum state, and then during this zone you should be equal to intake vacuum, and then right there the intake valve closes and we are compressing again. So this represents from here to here 720 degrees of crankshaft rotation and one camshaft event for both the intake and the exhaust. Okay? Now, I mentioned that we didn't get the cranking event, but if we saw, or if we had the cranking on here, what we would see is these peaks would be about double, right? Normal cranking compression is probably going to be, for a healthy engine, around like 120 up to maybe 140 PSI. And when you're looking at that, obviously compare that to specifications, but I mean, if I see something lower than like 90 PSI or something, that's not even, I mean, that's not really adequate for combustion, so that would indicate a problem right away. When you're looking at cranking as well, these events for the exhaust and intake will be much less defined. They're going to be really low, and you're not going to be able to see a whole lot of detail because we're not pulling in as much air as quickly. So you won't really get the details that you're looking for until you start idling and going into the higher RPMs. Okay, now that we're looking at this idle zone, our compression, I'm going to pull down this cursor, is around, it's 57. So the specification I usually keep in mind, it should be half of what your cranking was. So if normal cranking compression was 120 to like 140, then I'm thinking like around 60, maybe 70 PSI during our idle would be great. When you start getting in the range of like 40 PSI during idle, you probably are dealing with misfires, because at 40 PSI, that's not even enough compression to like get the heat that you need to break apart your hydrocarbons and stuff. So look for those kinds of things. Now, if I zoom back out here and we go look at this zone where I was holding it, right? Notice when I initially revved up to 2,500 RPM, we've almost doubled that. And then we settle back down and we're a little bit higher on our compression. And then our snap throttles were off the screen, right? The range that we picked of up to 200 PSI, it went over that. And keep in mind that your idle compression will probably triple during a snap throttle. So this looks completely normal. This is what we want to see. If you're not, right, if every time I try to snap throttle or I try to go higher in the RPMs, if my compression is not tripling or increasing like I expect it to, that indicates you have a breathing problem with your engine. Maybe a plugged up exhaust, maybe a plugged up intake, some valve issues. But like, just from being on this zoomed out picture here, you can see that this engine is breathing quite well. All right, now let's dive into a few more specifics. So let's zoom back into our idle range here. And to make this better for ourselves, we're gonna need some rulers. So I'm actually gonna pick one 720 degree event here, just like that. And now I'm gonna go over to rulers, and we're gonna turn on the phase rulers, and the more partitions you get, the more details on degrees that you can get. And notice I have that selected, the 720 degrees. So bare minimum 4 partitions, but you could increase this up to 8, all the way up to 12. So let's just do 4 for now. And now we'll pull those over. Okay, so I'll line up the first phase ruler at the top dead center mark right there. And then we'll pull over the other one to the other peak. Okay, so now we have something lined up at 0 degrees, 180 degrees, 360 degrees, 540 degrees, and 720 degrees. Okay, and that should be adequate for most things that you'll be looking at. Okay, now that I have those out, I love that you have this nice like perpendicular line that runs through your compression peak right here. And so it makes it very easy to be able to tell if it's even on both sides. You'll often hear the term like leaning towers when you're looking at this. You don't want to have any leaning towers, because if you have leaning towers, that means that your pressure that you're creating on one side is being lost on the other, right? They should, if whatever pressure I create, I should be getting rid of at the same pace. Okay, so look for that first, right? Make sure you don't have any leaning towers. This looks really good. So there's no indication that I'm losing compression right here. The next thing I look at is when right here where the exhaust valve was supposed to open, I want to see it like a pretty sharp turnaround right there. If this is just elongated and rounded, then that's an indication that your exhaust valve, right, maybe never even shut to begin with, right? We have a leaking exhaust valve. If we see a sharp turnaround right there, then that means that the timing and the way our valve train is working is really good, right? It's sealed, and then I have a sharp opening, and all of a sudden pressure starts to change. That's what we want to see right there. This mark here is, I told you, is our 180 degree mark. That 180 degree mark should land normally halfway up this exhaust ramp. So from the point where it opened to the point where it's fully opened, this line should be about right here. If you want to get more specific, I think most books or people say that it should be between like -10 degrees and 15 degrees of the 180 degree mark. So we could pull out these measurement tools and look at that right here. So that is, if I pick a middle point, so the difference between that middle point and the 180 degree mark is 19.68 degrees. So that's not normal compared to what the books and things that you might read say. But I will say this, on some performance engines and stuff, it's normal to see this within plus or minus 20 degrees. And this vehicle, I don't know if I'd call a Fiesta performance, but it is variable valve timing. So this is probably normal right here. Now, if this 180 degree mark is outside this range in this direction, then that would indicate that you have advanced exhaust timing. If you're over here excessively, then you have timing that is retarded back, okay? Next thing we look at is here during this exhaust zone. The reason we have these little bumps is because it's, right, you have multiple cylinders contributing to the exhaust. And so you're seeing like pulses and stuff from the other cylinders pushing and affecting the back pressure out here. So this is completely normal. Yeah. The next thing I'm going to pull this line down, and I'm going to put that to, I usually like to just put it at 0. Come up here, type 0, so that way it's perfect. And take a look at that back pressure. That back pressure should be like 1, maybe 2 PSI, especially at idle. So back pressure looks really good. I just did a car recently this week, and I'll show that at the end of this video, that had like 45 PSI back pressure. So that was quite obvious. It was clear up in this zone here. So anyways, this looks good here. Now around the 360 degree mark is when your intake valve is going to open. So your exact measurements, it usually opens around 15 to 30 degrees before this top dead center mark. So if I take this over here and I line that up at the 360 degree mark, and I'm going to pick, let's say 30 degrees. So somewhere around that zone right there, the intake valve opened. On some engines, when you're looking at this point right here where supposedly that intake valve opened, you might actually see like a defined, like a peak happening right there. But Other engines you won't. So it really just depends on which ones you're working on. So just know that it is happening a few degrees before that top dead center mark right there. And then the intake valve or the exhaust valve closes and we go back into this vacuum zone, and you have what we call the intake ramp. And so this intake ramp also has some specifications to keep in mind. So if we draw a line about halfway down this ramp, just like we did when we were looking at over here, it should be about 20 degrees past this 360 degree mark. Give or take, maybe, plus or minus 10 is normal, right? But this is where you can see intake timing. So if I'm too far this direction, then you'll have an advanced intake cam. And if I'm this direction, you have intake cam that is retarded back. Okay? The next thing I look at is down here, right? We reached a vacuum state when we were over in this zone, and now you're back into that vacuum state. Those two should be even with each other. So I pulled down this cursor, and you can see that it goes straight across. That's good. When these valleys that you're looking at, if they're quite uneven from each other, then we have some sealing issues. We have some valve issues going on that are changing our compression, our volume in the cylinder. Okay, so this one looks really good. And then over here, that point right there, that's what I was saying. That is when the intake valve closes and we start to build compression again. That intake cam closing event should happen, somewhere between like 30 and 60 degrees after the 540 degree mark. So you can check that. Now, mentioning back, when you look at cranking, a cranking waveform, since we don't have all this definition and stuff, like, you're really going to have to depend on when you see these opening and closing events happen to figure out if your timing is correct. Something to notice, like if you were in cranking, you got to remember there's not going to be as much vacuum during cranking. And so since you have very little vacuum during cranking, that's the reason why we're not getting the definition that we would expect here, because the differential between the vacuum and the exhaust back pressure will be so low that it's going to be down here. So like I said, you're going to need to know these specifications especially if you're checking this stuff during cranking. Now, something else to keep in mind, obviously this engine has VVT. And when you are looking at engines that have variable valve timing, right, you're gonna be seeing some of these things be slightly different, right? They're not gonna match every specification that maybe I've thrown out there or that you've heard from some other people. So that's something to keep in mind. And if we're in gear and we're revving the engine and stuff, then we're actually going to be able to see the timing change in relation to these degree marks, which is really cool. That's one of the more advanced ways to use this setup. One last thing to mention before we go look at some of the higher pressures here is you can also verify ignition timing with this. Right, there is top dead center. So if I pull out or pull over one of these rulers here to the spark event and line the other one up to that top dead center mark, we can figure out that spark is occurring 12.43 degrees before top dead center. So you could use that to figure out if your ignition timing is correct as well. Okay, let's zoom back out. And now let's zoom in on this 2,500 RPM range. Already the peaks are higher, we looked at that. But even more so, like, it kind of changes the shape of these, right? I can see that definition on the exhaust valve a little bit better. The exhaust plateau looks a little bit different. But you're still getting, right, you're still seeing all the same things. It's just you've got more pressures that you're dealing with here, more differentials, I should say. Let's go into even one of these snap throttles. Let's look at that. So now during the snap throttle, our compression is off the screen, and things are happening a whole lot faster. So again, we're losing a lot of the definition down in here. So when I'm looking at the snap throttle, I'm not using that really to look at cam timing or any of that kind of stuff there. I'm using it just to make sure that my engine's breathing well, right? Getting that triple the amount of compression that we had at idle. So when you're really trying to figure out if you have cam timing issues and things like that, go look at the idle. If you were trying to verify if your VVT is working, then put it in gear, rev it above 2000, and just see if those cam timing events change. If you want to see if you have good compression, then compare it from idle, from cranking up to snap, and see if you're getting all of those different things that we talked about. Okay, so I think I covered pretty much everything I can think of. Obviously, there's probably more that I missed. There's a lot that you can see in these waveforms. Very, very useful for diagnostics. Hopefully that helps you guys when you're looking at these things. I will say that this is one of the best tests, in my opinion, to really see engine condition. And it's great that it's non-invasive. You're not having to remove a whole lot, maybe just a spark plug usually. And so highly recommend using this for your diagnostics. If there's anything I need to add, or if you noticed something that I may have gotten wrong in that, let me know. But like I said, I hope that helps you guys. Thanks.